Now let's prove that Nash solution is symmetric. How do we prove that? Let's refresh the notion of symmetry. A bargaining rule F is symmetric, if you remember, if for any bargaining problem SD coming from the script B set, and for any permutation pi, if the permutation of the bargaining set S is S itself, and the permutation of the disagreement point D is D itself, well then the solution of this rule should basically provide the same payoff to all the players, I, J in N. All right, so that's what symmetry is. So if the game is symmetric, well then the solution must be symmetric as well. That was the idea. So how do we prove that? By contradiction. All right, so what am I going to assume? Well, I'm going to assume that the Nash solution is not symmetric. What does that mean? Well, that means there exists some bargaining problem, all right? It doesn't have to hold for all bargaining problems, but there should exist at least one bargaining problem, and there exists some, permutation. Oh, I'm sorry, that one is, I cannot change. So there exists some bargaining problem such that for every permutation, all right, we have pi of S equals S, pi of D equals D, right? If the game is symmetric, then the solution must be symmetric. So I cannot say the outcomes are not symmetric if I am looking at games where the game itself or the bargaining problem itself is not symmetric. So for that reason, I cannot say there exists pi. Okay, that was my mistake, and here is the reason. So the game must be symmetric at some symmetric bargaining problem. So the game is, I'm sorry, I keep saying game, but I mean the bargaining problem. The bargaining problem is symmetric, and this is true, and furthermore, f of I SD is different than f of J SD, well, for some I and J in N, all right? It doesn't have to be the case that everybody has a different payoff, but at least two guys have different payoffs, all right? So, without loss of generality, suppose that this is player 1 and 2. So I is 1, J is 2. Without loss of generality, okay? I don't know the identity of I and J, but I don't want to keep using I, J here and there. So let's say player 1 and 2's payoffs are not the same. So what does that mean? Oh, by the way, I'm looking for Nash solution, right? So therefore my rule is Nash. So let's use the notation N. So that means the Nash solution, the Nash payoff for player 1 on their game bargaining problem SD is different than Nash solution for player 2. Well, if they're not the same, remember these are real numbers, right? So if these are not the same, well then that means one of them is greater than the other one. And again, without loss of generality, suppose this is true. All right, so the player 1 gets a bigger share than player 2. What about other players? I don't know, I don't care, okay? So that's what it means if the Nash rule is not symmetric. Okay, this is what it means. All right, so what am I trying to do now? Well, from this, I will continue with logical deduction, and hopefully we'll come up with some contradiction. So here's what I'm going to do. Remember the game is, because the problem, the bargaining problem is such that satisfying the following: for every pi in S is equal to S, and pi of D is equal to D. I would like to deduct few things that hopefully will contradict something. All right, so what is that I can deduct? Well, remember D is a vector, right? D is a vector, something like D1, D2, all the way up to Dn. So for any permutation of D, remember, what is permutation? Basically, instead of writing player 1's payoff, I assign it to player 2, and player 2's payoff to somebody else, player 3's payoff to somebody else. So I basically reshuffle the payoffs, okay? So that's what permutated payoff means, if you remember. So for any permutation, permutation of the payoff vector D is D itself. What does that mean? Well, that means D1 is equal to D2, which is equal to D3, which is equal to Dn, right? I mean, otherwise, I cannot have this. I hope that is clear. If it is not, give yourself a moment. But if D is something like 10, 5, 3, all right, you know, any permutation of this is clearly not equal to D itself. It has to be that all the components of D are the same. Okay, I don't know if I'm going to use this. Probably I will. Well, what about this? Can I deduct anything from this? Well, S is not a vector. S is a set. Okay, so I can't really say, the set S is symmetric, but you know, I mean, the triangle we draw, 100, 100, 0, 0 is the disagreement point. So this is a symmetric bargaining problem S. And so I can't really say much about this, but I don't know. Hopefully this is going to be helpful. All right, what am I trying to do? So here, if you remember, the Nash solution for the bargaining problem SD is a vector N1 SD, N2 SD, all the way up to Nn SD. Okay, so here I assume that N1, for contradiction, we assume that N1 is greater than N2, right? So think of this as like 10, this is like, I don't know, 6, and whatever, the rest I don't care. So I'm going to consider the following permutation of this vector. The following one, let's call this pi n SD, which is basically the following, and 2SD, well, maybe I should get rid of SD part anyway, and 1SD, and the rest is the same, NNSD. Okay? I mean, this permutation pi, let's call it pi star. So pi star is the following guy. So the first guy is actually this, the previous second guy, and then the new second guy is the first guy, and everybody else is himself or herself for every I in set of players except 1 and 2. Okay, so basically I switch the first and the second guy's payoffs and keep everybody else's payoff the same. So therefore this becomes like 6, this becomes like 10. I mean, I give those numbers just so you can visualize what I'm doing. Everything else is the same. Well, what do I know? I know, well, first of all, this is in my set S. Well, in fact, this is, individual irrational payoff vector, which I know. Well, what else? We know that this is also in S. How do I know that? Well, because remember, the game was symmetric. Pi of S is equal to S for any permutation. So therefore, if this is in my bargaining set, well, this must also be in my bargaining set. What else? Well, if this is individual irrational, that means all those payoffs are greater than D. So all those payoffs are also greater than D. So here I am using this nice property that D1 equals D2 equals D3, which are all equal to D, let's say. So therefore, if 10 is greater than D1, which is D itself, 6 is greater than D itself, well, then this one is also. So therefore, these are all in this individual irrational set. Okay, where am I going through with this? Now, consider the following payoff. I don't know. Let's use the following notation, X star, okay? And X star is the following. Alpha times, instead of alpha, just 1/2 times NSD plus 1/2 times pi NSD. Pi and SD. Okay, so do you see what I'm doing? I'm basically doing that. I am taking a convex combination of these two vectors. So that's going to give me what? That's going to give me, 1/2 times n1. So I ignore SDs because it's going to take a lot of notation. Plus 1/2 n2, comma, 1/2 n1 plus 1/2 n2, and then n3, and then nn. Okay, because everybody else payoffs are the same. So I am just taking the convex combination of the first two guys' payoff. Well, why do I do that? Well, remember this was 10 in my simple numerical example. This is 6. So the convex combination is 16 divided by 2, 8. All right, so the first guy's payoff. And this is what? This is 6 plus 10, 16, 8. Okay, and everything else is the same. All right, well, again, where am I heading? Okay, this is where I'm heading. I started with this payoff vector, and then I basically take one permutation of this payoff vector. And well, I know that this permutation does exist in the set, my bargaining payoff set S, because pi of S is equal to S for any pi. And then I take some convex, a 1/2, 1/2 convex combination, or the average, arithmetic average of these two payoff vectors. And I know that this X star thing is also equal to my S set, the bargaining. Well, why is that so? Well, because remember, the bargaining problem is convex. So therefore, if one payoff vector is in set S, another payoff vector is in set S, any convex combination of these 2 points must be also in that set S. So therefore, X star is also in S. So what? Well, here's the thing. If you calculate the Nash solution with this X star, the value is going to be higher than this or this, because they have exactly the same value. So how do I mean, is it obvious? I don't know. For my numerical example, it's obvious, right? I mean, if you multiply, you're going to subtract each number with some di. So let's suppose, for simplicity, for our numerical example's sake, di is 0 or d is 0. So therefore, this multiplication is going to be 10 times 6 times all the payoffs, all the other payoffs. So it's like 60 times whatever. And this one is, again, 60 times whatever, but that whatever is the same in both of these vectors. Well, if I calculate the Nash solution for this payoff vector, however, not Nash solution, but this multiplication for this payoff vector, it's going to be 64 times whatever, and whatever is exactly the same as these two. And so these are 60 times whatever, this is 64 times whatever. Obviously this is higher, but that's a contradiction because remember, this NSD is the Nash solution. I mean, it maximizes this thing. But I just found X star, which gives a higher payoff than the Nash solution. So it's a contradiction. Here you may sort of object, well, do I know that this X star is an individual irrational? Well, yes, it has to be. How do I know that? Well, remember, all of those numbers are higher than D, so therefore their convex combinations will also be higher than D. I mean, if X is higher than D, Y is higher than D, these are numbers, okay? Well, then 1/2 X plus 1/2 Y is clearly higher than D, right? Equal doesn't matter, same argument. So, therefore, this is not only in S, but also is individually rational. Now I need to show that this this multiplication, when I use this payoff vector, is going to give us higher than those payoff vectors. So let's show that. It's very quick, I guess. And by the way, all of that caused because n1 and n2 are assumed to be different. So how do I going to show that? Well, I am multiplying this I from 1 to n, n1 minus d, n2 minus d, well, let's ignore this, times nn minus d. The d's are the same. On the other hand, I have 1/2 n1 minus d, 1/2 n2 minus, I have this. So 1/2 n1 plus 1/2 n2 minus d, right? This is the first payoff, times 1/2 n1 plus 1/2 n2 minus d times nn minus d. Okay, so which one is bigger? My claim is that this is bigger than this one. Okay, well, first thing first, all these guys will cancel out, right? 3, n3, n4, n5, there's no difference. So they're going to all cancel out. So all it matters is these two guys. Okay, so I need a bit more space. Okay, I cut some part of the videos, and so I just calculated this multiplication. So it's equal to this part. And this multiplication, it's equal to this part. And I claim that this one is less than or equal, less than this one. Well, these guys are going to cancel out. These square will cancel out. What else? I have n1 times n2 here. Okay, so I have n1, n2 here. And so I have 1/2 n1, n2 on this side, less than 1/4 n1, n1 plus 1/4 n2, n2. What do I want to do? I want to multiply both sides by 4. So I'm going to have 2 here, and then, those will cancel out. What else do I want to do? Well, I want to pull this guy to this side. Yeah, let's do that. And so what do I have? I have n1 parentheses n1 minus n2, and then there's another n2 parentheses n2 minus n1. We know that n1 is greater than n2, right? That was the assumption. So we send this guy to the other side. So it's going to be n2 parentheses n1 minus n2. Okay, good. What else? Well, remember n1 was greater than n2. They're not equal, so this is not 0, so I can cancel that out. And so n1 is greater than n2. Exactly, this is what we assumed. So what does that mean? That means literally this number is greater than this number. Well, what was this number? Well, this number is basically the Nash solution, the value of this maximization problem, all right? Well, what about this one? Well, this one, I instead used the vector x star, which was the convex combination of n1, two vectors, I'm sorry. So what I found is that there exists some x star, which is individually rational and feasible, which yields higher number than the Nash solution, which is a contradiction because the Nash solution should be the argument that maximizes this. However, I just found another feasible individual rational payoff factor, which actually leads or gives higher payoff than the Nash solution. Again, it's a contradiction. Well, what is the cause of this contradiction? It's the assumption that n1 SD is greater than n2 SD. So this can't be true. Can't be true. Remember, I said this is without loss of generality. What would be different if I said this? Exactly the same arguments. That would lead to contradiction. What if it is not player 1 and 2, but player 3 and 8? Doesn't matter, okay? So the identity of the players and which one is bigger than the other doesn't matter. If we have two negotiators whose Nash solutions are different, okay, well then we're going to have a contradiction. So this can't happen. Well, therefore, we have to have that the Nash solution must be giving exactly the same numbers for every I and j in N. Hence, the conclusion is that if the game is symmetric, well, then the Nash solutions will be symmetric as well. Hence, the Nash bargaining rule is a symmetric rule. Okay?